All right, so today we're gonna we already finished the math about big O last time. It's basically just brushing up about what you learned back in 1019, but we still get a chance to really reapply the concept over and over. So you definitely get a chance to practice more, which will be very nice, very practical. And so today we're gonna apply the math into the context of algorithm. I'm going to show you various Java codes, and we're going to figure out what's the asymptotic upper bound, the tightest one, the most accurate one, of course. We'll get there, but before that, let's see what you should be reminded. Your assignment number 1 was released for its solution. Just to remind you, you want to go to the E-class site for all the sections, not the one for X and Z, not that one, the common one. And for assignment number 1, I got 2 parts for you. You can only look at the source code, no problem. It's there, or you can also look at this one PDF file there where I got links to some solution video to walk you through the solution. I think for assignment number 1, I happen to have the tutorial videos available. So take a look if you need some walkthrough, or just drop by office hour to go over the solution with you. All right, so split array harder, right? I still want you guys to try before I release a solution. I'm definitely getting some good number of your fellow students from both sections to come to my office hour and share with me their solution, right? So if you want to talk about it, even though you have no clue, even that is okay, just come. And then it's good to talk about it before you see the actual solution. Office hour, TA contact, stay unchanged, just the same as before. All right, guys, any question about the course in general? Awesome. Let's now do a very quick recap about last Thursday, which was mainly about some properties of big O and the formal definition. Let's take a quick look. And then we're going to talk about various examples of applying the big O into coding, data structure, basically. All right, just give me one moment. There we go. All right, so last time we started with this visual summary just about the big O formal definition, right? Of course, you can go over the detail in the recording, but let me just remind you, whenever you want to recall the definition for big O, you want to think about 3 functions there. Function number 1 will be the f of n, which represents the runtime of some algorithm. And also the g of n will be the reference function, which we want to show that the big O family constructed on based on the reference function is going to be the family that f of n belongs to, right? However, just g of n alone is not going to properly upper bound f of n. You can see g of n here is strictly smaller than f of n in this case. So what we got to do is to apply some multiplicative constant that you got to choose in order to prove. Once you got that, you can see starting from this point over here, we do have the modified version of g of n upper bounds f of n. Right? So that's really the flow of thoughts that you want to keep in mind. Right? Just one example. And then we spoke about another alternative definition that's also going to define the big O formally using predicate logic. Right? I'll let you review it and let me know if you got any trouble understanding it. But just notice that here for the existential quantification, we say that if you want to show a proof, you want to find some witness of C and N0. That's exactly what we are doing, right? But we even got some proven strategy for you about C and N0, right? All right, so that's proven strategy if you got polynomial, if you got polynomial terms only about n to the power something. Of course, if you get log involved, then this strategy here will work almost always, but there will be some cases where it doesn't work. We showed you some example last time. So if you apply this proven strategy, you got to be careful. Always verify before you put that as a final answer. So you got to choose the C here and also choose the N0 here, always 1, right? Again, always verify. And we talk about 2 cases over here to prove about f of 1 and also f of n, right? So these 2, right? You can go over the details in the proof. We kind of did it from scratch. So if you got any trouble understanding it, let me know. Question?
What if G is already an upper bound on Fn before you add a multiplicative constant C?
Oh, good question.
Is it possible that C could be a fraction?
Interesting. Okay, sure. So let's say, well, just in general, right? Let's say f of n is here, but let's say f of n exactly g of n, let's say. If they simply overlap, in that way, you can just choose the multiplicative constant to be 1, right? That'll be fine. Unless you have some specific example thinking, but we can discuss maybe after class to see what specific example you're thinking. But in general, g of n alone may not be sufficient to upper bound f of n. That's a principle. If it's not sufficient to upper bound f of n, then you have to choose the c appropriately. Okay. Very good. All right, so that's a proof you guys can go over, right? Just make sure you kind of follow through the step and see the insight, right, about the two cases. And we did this example here just about using the strategy, right? You can review it. And we talk about like a different properties for big O, right? It's just about individual family. Let's say big O of n. So that means all the functions that has strictly lower or the same power as n, they should be included. For example, n to the power of 1, just the same power. And also all the functions that will grow no faster or just grow slower, right? Grow more slowly than n, right? You can see, for example, n is over here, right? This one here. What will be the function that grow more slowly asymptotically than this? It will be the function itself, which is over here, and also, for example, logarithmic and also constant, right? You can also view, kind of try to link the observation here to the diagram here. And it's also very normal for a family to contain another family, right? So you can see big O of n squared will contain all the functions that belong to big O of n, right? That's also something we said. And the next one we talk about is how to relate different families, right? So the proper subset should be the way to go. We kind of review very quickly about the proper subset. You guys can take a look. But if we apply that concept into the big O, for example, let's say we got the smaller family linear, the bigger family quadratic over here. So that means proper subset tells us there should be at least one function here that can be upper bounded by n squared, but it cannot be upper bounded by n, right? We kind of spoke about it, right? I gave you some example, let's say here, right? You guys can take a look, right? So if I give you different combination of the family and ask you to kind of justify why one function cannot be upper bounded by some family function, then you should really be able to do it, okay? So this example here, simple, but you want to make sure you understand what's going on there. Well, so that's the final summary just about the different families over here, right? So we got gradually increasing sizes of the family here, from the lowest power to the highest power, right, over here. And you should be able to figure out example, for example, some function here that can be upper bounded by this, but not upper bounded by that, right? So this will be one member here, right? Like a proper subset. Okay. All right, so we talk about being correct versus being accurate, right? For example, let's say 7n minus 2. You can see that one situates over here, n to the power of 1. However, you can also say this is also a member of the larger family, which is n squared. You can also say correctly that it's a member of this even larger family. It's correct. However, if you're not being accurate, you might run into misleading judgment, right? That's something we said earlier on Thursday. You can look at these two functions here, and then I simply gave you one example where I gave you the correct bounds, but they are not exactly accurate. You want to see why? Is going to lead you to some misleading, like an incorrect decision, right? Because every time if you're comparing two alternative algorithms, you should really choose the one that's going to be asymptotically slower, all right? Or lower power asymptotically. Yeah, make sure to review this example here. And we talk about whenever you want to present a final answer, you should really make sure you don't include any multiplicative constant and also lower term. However, for intermediate calculation, it's okay. You will see that when I solve the problems with you today, you're going to see for the intermediate calculation, I always include things like that just to show you the intermediate work. But for the final answer that's going to be, for example, graded, should be like this. All right, just make sure you explicitly mark to say this is the answer I want to present as a final answer. We'll see. Okay. All right, and then we did a series of examples. So you can think about this example here, just mathematical, what you could have done in 1019. You're given some function here, and then I want you to, number one, determine what's the most accurate asymptotic upper bound, and then prove it, right? Just mathematical. So we did several examples there, and guys, please give a try for exercise, right? You can find the answer also on the slides. If you want me to show, if you want to show to me your work to get some feedback, you can also drop by. That's not a problem either. And example 3 here is very important because that one involves not just polynomial, it involves also log. So that means our proven strategy may not necessarily work right away, right? May not. It may work if you're lucky, but it may not work. So that's why you have to double check when you actually got n0 equals 1, once you have chosen the C accordingly. So in that case, verify actually failed. So that's why we're going to try another n0 equals 2. So typically, if 1 doesn't work, try 2. 2 doesn't work, try 3. It wouldn't take too long for you to get a correct answer. Okay. And then, yeah, this one will be for exercise. And this one this one also exercise, right? Right, that's about it from Thursday. Any question? All right, as I said, from up to next Thursday is mainly just some review about the relevant parts you will need from 1019 about big O. And for the things about proper subset, things like that, they're very useful stuff. We'll still get to them, once we get to different parts of the course. But for big O, it's really important for you to grasp the idea. And for today, we're going to start off at the last part of the asymptotic analysis lecture. Okay, so you will see that from slide number 32. All right, slide number 32. I got 5 examples there, I believe 5, right? Around that number. 5 examples there, basically 5 pieces of Java code. We're going to look at each one of them. We don't really try to understand the logic of the code, although they're quite easy to understand, but that's not the point. The point is you can try to derive the asymptotic upper bounds or to approximate the bounds without understanding the logic. We're just going to look at the code line by line. Whenever we got loops, that's going to be the trickier case to think about. I got 2 tricky examples for you for today. We're going to solve them together for you to get a feel. If we got time, we'll move on to the new lecture just slightly, hopefully just like the morning lecture, the morning section. All right, so now I'm going to just, for the slide, you can just go all the way to the end. I got 5 examples, right, until the end. Let's now take a look at the iPad, right? I got all the examples here, one by one. The first 2 examples just for warming up, right? Just for you to really see the transition here. We are not really dealing with pure mathematics anymore, not really. We're trying to apply the math into the context of software development, coding, okay? Let's say we got this piece of code over here. And the question is, determine the asymptotic upper bound. I should really say the most accurate, the tightest. Otherwise, you can simply say it's big O of 2 to the power n. That's correct, but it's not the tightest, right? So what I want is the tightest asymptotic upper bound. And also notice one thing here. We are trying to determine the asymptotic upper bound. That means we are somehow approximating. Okay, it's important to see when we say we want to determine the bound, that means we are really approximating. We are not really counting the number of primitive operation precisely. So versus counting. So this is approximating the number of primitive operations. So these 2 are both valid tests, but now we are not focusing on this one here. I'll give you guys some extra practice maybe later when we're getting closer to the written test number 1. Okay, but let's focus on this, approximation. So for the first 2, I'll just go over directly, right? I'll give you guys a little bit more chance to maybe share your thoughts, maybe a little bit later, once we get to the trickier example. All right, we're going to analyze line by line. Line number 1. If I look at this line here, I can see that I got a variable assignment. Well, just 1, right? So I'll just put 1 here. 1 here simply means it's a constant, it's a line that will take a constant amount of time. And this one here, also 1, because I got just relational operation, just 1. And this line here, just 1, just variable assignments. And here, just 1, just return. Very straightforward case. If I want to determine the asymptotic upper bound, it would just be, I'm going to do some intermediate work. So I got 1, 1, 1, 1. So you can say this one is for line number 2, this one for line number 3, line number 4, and also line number 6. Okay? And I can simplify that a little bit. It's going to be 1, 2, 3, 4, which will be 4 times n to the power of 0. So I can now, highest power is 0, drop the multiplicative constant. There's no other lower term. So this one should be, finally, big O of, you can either say n to the power 0, or you can say big O of 1. Either way works. All right, so this will be the answer for the first problem here. All right? All right, should be straightforward, right? Question?
You know how you did the whole proof for the other cases?
Uh-huh.
How does that work if it is constant? Like, do you bother? Or
Sorry, say it again. I don't quite capture.
The whole
Uh-huh.
How would that work?
So, okay, so here we're not really doing any proof. So here we're just trying to approximate the number of primitive operation line by line. And then we kind of sum them up to really give the asymptotic upper bound. That's what we're doing. So whatever you come up with, for example, big O of 1, you don't have any further proof to show. You can think about what we did earlier on Thursday last week, is to say if you are given some function there, and then how do you prove that this function is the family of some big O? It's a different problem. Yeah, okay, good. All right, let's now see the second one. Okay, the second one also is quite familiar to you. This one here is a find max. So what we did earlier was we tried to calculate precise number of primitive operation. And we got something like a 7n minus 2. Right, so this one here, you can see obviously, if you say big O of 7n minus 2, that's not acceptable. It should really drop and drop. So you only got big O of n. Right? That's one way to solve it, right? To count the precise number of primitive operations. But let's now try to solve the same problem here slightly differently. So now we want to approximate. We're going to go line by line. Okay? Line number 2, you can see we got array indexing. I got also variable assignment, but I'm not going to put 2 here. I'm only approximating. Whenever you think it's only a constant number of primitive operations that does not depend on the input size n, you can just put 1. So what I put 1 here really means like a big O of 1 over here. And then I'm going to look at this part over here. All right, so this part here, I'm going to figure out how many iterations are there. So here, what we said earlier, precisely should be n minus 1 iterations. So now we are approximating. Doesn't really matter if you think about like an n minus 1, n plus 1. Doesn't matter because they will just be big O of n anyway. So I'm going to say n iterations. And then I know that the body of the loop is actually going to be here. What about the body of the loop? I'm going to look at line number 4, 5, and 6 together. I got primitive operation. I got primitive operation. I got primitive operation. I got another one here. I also got maybe a bunch over here. But I still got a constant number of primitive operations. I don't need to be bothered about precisely how many because I'm only approximating. So I'm just going to put 1 here. That means every iteration, I'm only going to execute a constant number of primitive operations. That's what I'm talking about. All right? And then outside the loop, line number 7, it's just a return. So that'll be 1. All right, so that's how I analyze line by line. And let's now sum them up together. Big O of, I can say 1 here plus n multiplied by 1 plus 1. Okay, I'm going to annotate that a little bit for you. So think about 1 here is line number 2. And this one here, based on line number 3, about how many iterations we have. And the 1 here is about the body of the loop, which will be line number 4 to line number 6. And the final one here will be line number 7, right? And do a little bit of calculation. It's going to be n plus 2. Not exactly 7n minus 2. That's okay. 7n minus 2, n plus 2, they belong to big O of n anyway. Right? So approximating is not going to give you the wrong answer. That's a bottom line. All right? And this one here, if I just drop all the lower terms, for example here, I'm just going to get big O of n. So that's the final answer. All right? Well, approximating. Okay. Of course, if I ask you to calculate the precise number of primitive operation, it will be another task, which is different, right? Just don't get confused on that regard. All right, any question? All right, let's get something slightly more challenging, slightly, okay? This one here. All right, why don't you guys take a look at this fragment of code here. You don't necessarily have to understand exactly how that works, but that one should be maybe something you have to, maybe you did already in the first year or second year. Take a look. I just want you to guess what should be the tightest asymptotic upper bound. Just take a guess. And then we're going to derive it after that. All right, any guess? N squared? Any other answer? Okay. for those of you who might be thinking, oh, since I got nested loop, so I should get n squared. For this question here, you're lucky, that's right. But watch out. Getting nested loop doesn't really mean you get n squared all the time. I'll prove that you're wrong, okay, in the next page. But for now, you might be the right guess. The guess is right, it should be n squared. But let's now work out exactly how to derive. Because the loop pattern here may not be exactly like this, like it's this straightforward to figure out. So that's something we've got to dive deep into. All right, and of course, in the exam, or I'm not sure, maybe not the written test, but in the exam, if you simply say it's big of n squared, it might be okay for part 1. But for part 2, if I want you to show the detailed work, you're going to show what I'm going to write, okay, from scratch. That's something we're going to spend some good amount of time today to talk about. All right, so let's now analyze the code structure a little bit, right? And then we'll do the math. Okay, so first of all, let's now box this particular header over here, right? So this is the nested loop that we're talking about. And we got 2 loop counters. So I'm going to use blue for I, initialize to be 0. I'm going to use the purple for j, initialize also to be 0. So I and j somehow are independent, somehow, right? But there could be cases where j might depend on I or vice versa, but not in this case. So it's a simpler case. I want you to look at, first of all, this block of code, just this block. So I'm going to just highlight them. So the one I'm going to highlight in green, one here, and one here. These 3 lines, okay? I'm going to call this phase number 1, P1. So I'm going to write some annotation there. Think about this part here. I'm going to call them P1, 3 lines. Line number 4, 5, and 6. P1. Now you want to think about how many times exactly P1 will be executed, right? Now I'm making the assumption that you guys know about how the nested loop should be executed or the control flow should really go very well. In case you got trouble about the control flow, you should really reach out to me, right? Because that's a very important assumption also for this course. Assuming that's the case, I'm going to put down here. So P1, which will be these 3 lines, gets executed for every combination of I and j. And I'm just going to put in this format, I and j, right? It's more like a pair, right? You're going to figure out somehow how many combinations are there, right? In this case, it's actually quite easy, guys. Any idea, intuitively? How many combinations are there for I and j? N squared? Yeah, that's pretty right, but we're going to see exactly how to derive that, right? We'll get there, okay? It's a good guess, but we're going to show that the guess is actually right. And then, since we know that, we're going to figure out exactly how many combinations are there for I and j, and then each execution of this block is going to take how much time in terms of the number of primitive operation?
We can just approximate that block to 1, and then 4 would be n.
Yeah, that's good. So we can approximate somehow this block to be 1, just like how we did it earlier, right? So you guys can think about, I got constant, 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 and constant. All constant added up, right? So I can safely just say this part over here is just going to be big of 1 for each execution. And then once we figure out exactly how many combinations are there, we're just going to multiply these 2 numbers. But we'll get to this part here in just one moment. Okay? All right, I'm going to look at phase number 2. And I'm going to look at, okay, let me highlight in blue over here. Okay, I++. That one there, how many times exactly would that be executed? You can see that one there, if you look at the brackets a little bit more carefully later, this one here, I++ is outside the inner loop. So that means I++ will only be executed for every iteration of the outer loop. That's something you can double check, right? So I'm going to write here to say phase number 2. Okay, phase number 2. And then that one there is also going to be big O of 1 for each execution. because it's only some primitive operation. And then I'm going to make some annotation here as well. And also P2 gets executed for every value of I. Right? So to figure out the value of I, you only need to look at the outer loop header, right? And of course, you can see outside the nested loop, we actually got this line here, the return. That one there, big O of 1. Big O of 1, right? So we're pretty much there, except that we need to figure out exactly how many combination of I and J. Okay, we got to figure that out. We'll get there. So to do that, I'm going to just elaborate on the patterns about a loop counter. That's something we're going to analyze. So it's a very general approach. It doesn't matter how the loop is going to set up. Maybe you got different nested level. Could be triple nested loop or 4 nested loop. Doesn't matter. You just have to enumerate somehow all the possible combination of the loop counter. Right? It's a very general approach. So I'm going to put here to say patterns of loop counters. Over here. All right, let's now start with the outer loop, in which case it's going to be I. I is going to be from 0 all the way to, remember, n minus 1, right? So when we talk about iterations, when I reaches n, it's going to make it false, and we exit from the loop. So that value I equals n doesn't count, right? It's an iteration. So if you look at think about it like a 2-dimension, like a matrix, right? So you can think about I here is going to be starting from 0, 1, 2, all the way to n minus 1. All right. And this part over here is about the outer loop. Runs. And how many iterations are there? So we basically go from I equal to 0 all the way to I equals n minus 1. How many? And this one, you got to be precise, okay? And why n? All right, so I'm going to give you guys a little bit formula here, which you might find handy for later, okay? I'm pretty sure you have seen something like this, maybe in your previous calculus class, something called closed interval. So if I got a closed interval, I got value A and value B, right? Presumably A is less than equal to B, right? How many integers are there in this closed interval? What's the formula? For example, if I got, let's say, I want to calculate how many numbers are there from 3 to 99, inclusively. So 3 should be included and 99 should be included. So what would be the way to calculate? If you say 99 minus 3, okay, is that correct? No, how many numbers are there in the interval? And 3 and 99 are included. So think about this. Okay, you can change your answer, that's okay. Maybe I wasn't clear enough. We got 3 here, and then we got 99 here. We want to figure out, starting from 3, ending with 99, how many numbers are there in this interval? So 99 minus 3 plus 1. All right, guys, that's important. If you got trouble understanding that, you can reach out to me. But I'm going to assume it's easy for you to verify. 99 minus 3 plus 1, because you want to make sure this one is also counted. Okay? In general, if you got this one here, closed interval, it's going to be B minus A plus 1. Okay? It's going to be very handy for us to figure out how many iterations there are for the loop. Okay? And in our example here, for example, we got, let's say here, we got from 0 to n minus 1, right? Let me put it down. So if you got 0 here to n minus 1, right? So this will be how many integers? It would be n minus 1 beginning minus the end plus 1. That's exactly just n. Right? Easy to verify. This will be, okay, so b minus a plus 1 integers in the closed interval. Let's be precise. In the closed interval. Including a and including b. All right? Let's assume we understand this already, so let's now apply that, right? So this one here, let me just write from 0 to n minus 1. We know that this one is going to be n iterations. right? So this will be what we can conclude from just the first dimension about the I, the outer loop. So the outer loop is going to run exactly n times. For each iteration for the outer loop, we also need to execute the inner loop over here. So let's now figure that out. When I is equal to 0 for the first iteration, how many iterations are there for the inner one? Also n minus 1, agree? Because, also n, okay? Because we're also going to try the value for j equals 0, 1, 2, all the way to n minus 1. So the way to present this is like this. So we're going to get j here is going to be 0, 1, 2, all the way to n minus 1. All right? And this one here, we know that is n iterations. Similarly, for the second iteration, for outer loop when I is equal to 1, we also get j value will be 0, 1, 2 always, right? As you can see, the way we kind of bound j is always from 0 all the way to n minus 1, so the same. So let me complete that. 0, 1, 2, all the way to n minus 1. So that's also n iterations. 0, 1, 2, all the way to n minus 1. That's also n iterations. How about the last one? Also the same, right? I'll get to you. 0, 1, 2, all the way to n minus 1. And also n iterations. Question?
If instead of j is less than n, it was just like, it was always j is less than 3, for example, would that still...
That's a very good question here. Your fellow student question was, what if, let's say here, the upper bound here, rather than depending on the input size n, what if it depends on some fixed constant? Save that question there. That's exactly the next page I'm going to talk about. So that's also a very good one to talk about. When you actually got nested loop, it doesn't really mean n squared always. We'll get there. All right? Good. All right, so we got here, we got n here. So now we want to figure out so for each one of them, for example, I'll give you one example here. So let's say this one here. Oh, how about this one here? This one here, for example, what this cell really means is the ij will be simply 2, 1, right? The combination. This one here is when phase number 1, which is over here, executed just once. And out of this matrix over here, how many cells are there? Right? We got n columns in each row, and we got n rows, n times n. Right? Okay. So overall, we actually got n times n cells in the, you can say matrix or just 2D, right? And so n over here will be the number of possible I values. And the n here will be the number of possible j values. So they will add up very nicely. So which will be n squared. Okay. So now we got everything we need. So we're going to derive the final answer and then see. Yeah.
If we ever ask this on a test, would we have to use, show all this side work?
Yeah, so I think this side work here is pretty important, right? So for example, let's say in the exam, I might give you something this basic. That's great. You can easily show that. It should not be a problem. But I think that there will be some loop counter pattern there that might be more sophisticated. I think doing this side work might be very beneficial for you anyway. So you want to show that. Yeah, for sure. Yeah, we're going to see some example very soon. Just another one that's slightly trickier. All right, so let's now figure out exactly the running time. Big O off. All right. First of all, I'm going to calculate this part over here, right? I know that the number of cells over here in the matrix will be n times n, which will be n squared. So n squared over here is the number of ij combinations. And for each combination of I and j, I'm going to execute this part of the body of the inner loop, which will be phase number 1. And that one there is just 1. Okay, so you can think about that one is multiplied by just 1. And that one there is basically from line number 4 to line number 6. Right? That's the most complicated part, actually. And then what about phase number 2? That one there is going to be the number of iterations for the outer loop, which we know is simply n. Right? N here. And then we're going to say n times also 1. So this will be the number of I values for the outer loop. And the 1 here will be just for line number 7. Okay. And finally, you can see outside the loop, we also got return false, which is also 1. All right. And let's do a little bit more calculation. It's going to be big O of n squared plus n plus 1. And easy. Drop all the lower terms. No multiplicative constant for us to drop for the highest term, n squared. So that'll be the final answer, which matches our guess in the beginning, which is good. So that's the final answer. All right, any question? All right, if no question, let me respond to your fellow student about what if we change the bound. For example, rather than something that depends on n, we change to maybe some constant, potentially large constant. Is it going to change the running time? The short answer is yes. Okay, let's take a look. So I'm going to give you 2 variants over here. Okay, so let's say I still got my contains duplicate from the previous page. I just got 2 duplicates over here. Right? Variant number 1. I'm going to modify, let's say, here, rather than here, n, why don't I say 10,000? Or some large number, doesn't matter. 1 million, doesn't matter, just some large number. So now, after this, are we still going to get n squared? No, because easy. So if you go back here, you can see this is the highest term that's going to dominate. And n squared comes from the number of outer iteration times the number of inner iteration, right? So here we got n times n. How about now? 10,000 times n. Agree? So that one is going to dominate. Okay, so we only need to look at that one. So that one there, if you think about big O of 10,000 times n. Well, the highest power is n. Multiplicative constant can be drop. Doesn't matter how large it is. Doesn't matter. Asymptotically, any large constant is small. Okay? What we get is big O of n. Okay, not n squared. Okay, so that can maybe somehow answer your question, right? Let's play a little bit more. Can I make this loop potentially even more efficient? Make it constant. Oh, I can. Why don't I change the other bound also to be constant, right? I can say, for example, this one here, 1 million. Here, also 1 million. Sounds big. Asymptotically speaking, they are not big. So what I would get is big O of basically 1 million times 1 million. Basically, think about this is like a big O of some very large constant c times n to the power of 0. Right? And I can always drop multiplicative constant, no matter how large it is. So this will still be just big O of n to the power 0 or just 1. All right. Yeah, so hopefully these 2 variants kind of convince you that whenever you see the code that you're supposed to analyze for the asymptotic upper bound, don't just to see how many levels of nesting you are having. That's not the way to go. You really have to see how the loop counters are changing between the iterations and count. Okay? Any question? Yeah?
So say we have an algorithm that has 2 loops, a nested system with 2 different counters, like we have one m and one n. Mm-hmm. Would that, instead of being O of n squared, be considered O of n?
Yeah, exactly. So what your fellow student was asking is another very valid question here. I'll answer that briefly. Okay, we wouldn't see that many example here because usually we are considering just one input size n, right? Let me put that anyway. But it's a valid question, which I like. Give me just one moment here. Let me close it. Oh, let me copy it again. So what I would do is I'm going to, copy. There we go. Wrong button, I guess. There we go. Okay, this one here. So let's say we still, let's say it contains duplicate, right? Let me introduce another array. let's say we got, so n here is really a dot length. Okay, let me extend the parameter list over here, right? I might say there's another integer array, maybe b, like an independent array, okay? And then I may introduce maybe integer m, just for convenience. So over here, you can think about the m here is really the length of the second array, b dot length. Okay, thinking that way. So now I can say, of course, you can change the name. The name doesn't really make sense anymore, but that's okay, right? We'll just keep that. So let's say we change this one to be, this is still n, but we modify this one here to be m. Right? So we got different bounds over here. So what we're going to get will be ultimately just big O of n times n. Your fellow student was asking, would this be just the same as big O of n squared? No, not really, because we have no idea what's the relationship between the sizes between this array here and this array here. So for this question here, it will be sufficient just to say n times m, where here we know that n is the size of one input and m is the size of the other input. So this will be more accurate way of saying things over here. Okay. If we get into something like this later, I'll let you know. But hopefully that can answer the question. All right. Next one. All right, so this one is pretty easy, but let's now let you take a look at that for one moment and let me know what's your guess. All right. Oh, we got 3 loops over here. Should that be n to the power 3? No, obviously not, right? Good. What should be the tightest asymptotic upper bound? N squared? N squared? Okay, good guess. Okay, let's now take a look very quickly. Okay, n squared, yes. All right, very quick. Line number 2, just 1, right? Just constant operation. And then if you look at the first for loop, that one there looks linear because the loop, I counter will just go from 1 all the way until maybe n minus 1, still n. And this one here is outside the loop, but that one there also just 1. And if you look at the nested loop over here, very similar to the contains duplicate case, you got n here, so that should be n squared. And finally, you can see this one here is just just 1. So what we get is big O of 1 plus n plus 1 plus n squared plus 1. Big O of n squared plus n plus 3. And you can drop the lower term, n squared. Okay. What this one tells us is the part of the algorithm that has the highest power is going to dominate the running time. Right? That's another way to see it. And of course, this one here is the most expensive part for the algorithm. Of course, it's going to dominate asymptotically. Alrighty. Final problem. All right. You guys were asking about, maybe you asked about how to change this, maybe I and J. Maybe I ask you, right? There you go. Okay, guess first. Well, I highlighted the tricky part for you already, right? You can see for the inner loop, J does not start from 0 anymore. It starts from the current value of I, which might give us some advantage, right? Because we know that gradually I is going to get larger and larger. Let's say when I is equal to n minus 1. In that case, J is going to be n minus 1, and n minus 1, just one iteration. It sounds to me, it's pretty efficient, right? More efficient than the previous one contains duplicate. It sounds to me. Or you think you're being misled?
Would it be n log n?
N log n? Typically, if you only got addition without any multiplication or division, you wouldn't get log n. Not really. Good guess. Okay, but you're claiming that it's going to be cheaper than n squared. Okay, sure. Or any one of you was somehow convinced by me it's going to be n. Nobody. I'm glad. Good. Anyone? Any other answer? Just guess. Go ahead. N squared by 2? Well, n squared by 2, n squared, right? Okay. It turns out this one here remains to be n squared, even though in the later iteration for the outer loop, I value is going to get much larger than the beginning, which will reduce the number of iterations for the inner loop, but that one there wouldn't change what's going to be derived asymptotically, right? It sounds a little bit weird right now, but we're going to show that to you. So if you only guess big of n squared, that's good, you had the right guess, but we're going to show exactly how this can be derived, right? We're going to see that. All right, so this is something we're going to follow the same approach to observe the loop pattern. But before that, let's do some quick annotation. So we're going to focus on the loop header. So we're going to focus on this loop header here in just a moment. Okay, we're going to do that. Okay. Before that, outside the loop, we got line number 2. This one here should be just 1. Right? Also, outside the loop, over here, return, that one should be also 1. And then, if you only look at line number 5 alone, that one should be just 1. That means every time you try to execute it, it's going to be 1, right? But how many times are going to execute it? It's going to depend on how many combinations there are between I and j for the nested loop. Always depends on I and j combination, okay? So here, you want to, okay. This will be it will take 1, like a constant number of operations for each execution of ij, for each execution of I and j, right? That's important to know. So now we got to figure out exactly how many combinations there are for I and j, right? That's something we got to figure out. Let's now try to observe the pattern. So pattern of I and j. And since the outer loop has I, so we're going to start with I, right? That's the first dimension. I will be from 0 all the way to n minus 1, the same as before. That one's straightforward, okay? So I'm just going to use, again, the blue for I, and also I'm going to use the purple for j, okay? Here I, and also here will be for j. Okay. All right, so I got I here can be 0, 1, 2, all the way to n minus 1, okay? And now I know pretty well the number of iterations will be from 0 to n minus 1. That's a closed interval, right? And we know pretty well by the formula is n. Okay? Let's now figure out a second dimension. That's going to be trickier, okay? If you think about it, let's say here, j. Let's say when I value is equal to 0, what would be the range of j? 0 to n minus 1, right? Okay. So here, since we're counting, so here this part we're going to be more precise. J will be starting from I value. In this case, will be 0, 0, 1, 2, all the way to n minus 1, right? You can see strictly less than n, right? Should be n minus 1. And what about when I value is equal to 1? Start with 1 all the way to? Yes, exactly. The upper bound doesn't change. It's really the lower bound that's actually changed, right? Very good. So it's going to be 1, 2, all the way to n minus 1. And for the next one, I'm not going to bother you. 2 all the way to n minus 1. And also, what about the last one? N minus 1, right? Good. And you guys can see that we got some very nice triangular shape over here. Exactly here, right? Over here. Which is good. All right, and we're not done yet. Somehow we very carefully enumerate the combinations of I and j, but now we got to count exactly how many combinations are there. So for row number 1, how many combinations do we have? We got 0 all the way to n minus 1, right? You can write down the closed interval over here. So I'm going to use a different color. So it's going to be from 0 to n minus 1. We'll know that it will be n. For the second row, is from 1 all the way to n minus 1. So it will be n minus 1 combinations. And then for the third row, it's going to be from 2 all the way to n minus 1. And then it's going to be n minus 2. Basically, the number of combinations are decreasing, simply because the value of j is increasing, right? Symmetric. And you go all the way to the bottom here. The bottom line is going to be from n minus 1 to n minus 1, just itself, one value. So what we got to calculate would be n plus n minus 1 plus n minus 2 all the way to 1. Does that kind of seem familiar to you? By the way, this kind of summation here has a name. Huh? Not factorial, not quite. If you say n times n minus 1 times n minus 2, yes, but now we say plus. Let me write it down. Okay, I see the way the confusion might be. So if we want to calculate the number of combinations, it's going to be n plus n minus 1 plus n minus 2 plus all the way to 1. If I change this to be multiplied, of course that will be factorial, but it's plus. Nope. There's a name for this summation series here.
Arithmetic series?
Arithmetic sequence, thank you, or arithmetic progression, right? Either name. And I'm pretty sure you have heard about this name before. I'm going to review the sequence very quickly to tell you the formula you also need. But I want to give you some heads up. The arithmetic sequence is the easy one to really kind of remember. It's asymptotic complexity, right? I mean the asymptotic upper bound. There's another sequence called geometric sequence. That one there we also need, but when we talk about trees, not yet. I just want to give you some heads up. I'll talk about geometrical sequence and also give you some nice proof about it very soon, after the reading week. All right, so let's now talk about arithmetic sequence, right? Very quickly. I'll just give you the facts, right? And I'm not going to worry too much about how to prove the formula. If you're interested, we can talk, maybe beyond the class, okay? So this will be the general form for the arithmetic sequence. You got I here plus I plus C plus, let me write down the whole thing and then I'll explain. And then I plus 2 times C plus all the way to I plus n minus 1 times C. All right, so let's now recall the terms. The first one here, the leftmost term, is called a star term. And I can rewrite this slightly, which will help for some later question. Think about this one here is more like I plus 0 times C. It's going to be 0 anyway, right? And then the C we're talking about over here is something called common difference. All right, and then, okay, that's good. Another term we gotta also figure out is how many terms there are in this sequence over here. The number of turns. Guys, in this sequence here, how many turns are there? N, precisely, right? Do you guys know how to figure it out? See the pattern here. We start with 0C, 1C, 2C, all the way to n minus 1. So we'll get to the closed interval between 0 and n minus 1. We've got n turns, right? You got to be very kind of proficient in figuring out things in the pattern. It's very important. Okay, it will be n turns. All right? So now the formula for the sum is going to be the following. Okay? You're going to sum up the beginning and the end term. So I over here plus I plus n minus 1 times C. And then multiply by the number of turns divided by 2. All right, I'm going to draw you some connection here. So this one here is a beginning term. This one over here is the end term. And also, what we just figure out over here, n is the number of turns over here divided by 2. All right, I'm just going to give you the simplification of that. You don't need to worry. You can take it for granted. This one is going to be C times n squared plus 2i minus C times n divided by 2. Right? But if you look at this, what's the highest term? highest power, n squared. So that means the big O of n squared. Okay, that's a conclusion. So if you got a geometrical sequence, if you got an arithmetic sequence, it's going to be big O of n squared. Okay, like this form. And let's now go back to where we were over here, right? So for this particular one, how do we figure out the sum, right? You're just going to say the beginning, which is n, plus the beginning term, the n term over here, multiplied by the number of terms, which will be n, right? We go n all the way down to 1, so that's n terms, divided by 2, right? So that one there, obviously, should be big O of n times n squared. That's the highest power, right? N squared. So this is the very important intermediate result that we figure out about given this nested loop, what will be the number of combination between I and j, okay, n squared. All right, so now we are ready to put everything together and figure out the answer totally. Big O of, so we want to do the 1 here. So this is line number 2, the sum initialization. And also plus, we got n squared times also 1. The 1 here is line number 5. And also the n squared over here is the number of ij combination. That's something we just figure out. And also plus, also got 1, which will be line number 6. Okay, let's do a little bit simplification. Big O of n squared plus 2, right? Drop the lower term, we got n squared. Right? So our initial guess was also right, but you want to show this intermediate work. Okay. All right, so that's the final answer. All right, any question about this? Good. All right. If no further question, I would suggest that okay, this one's good. Okay, this one's good. Okay, let me do, I got about 22 minutes over here. I would suggest that we take a very short break, 2 minutes, and then we're going to continue and talk about a new lecture. I want to do at least one example today, right? Okay, let's get your iClicker ready. So now we are done with the asymptotic analysis lecture. You can review it and let me know if you got any question. So let's now move on to a new lecture, okay? So this lecture here, the main part should be about the linked list, but we will not be able to get there today, I'm afraid, but definitely, hopefully Thursday in the later part. So this slide here, let me give you a very, oh, you know what? Let's look at the learning outcome, so we'll see, okay? We're gonna learn about, first of all, the basic data structure, arrays versus linked list. So these two are the basic building blocks for any algorithm that you have to implement. For example, if you want to implement a queue or a stack, you have at least these two choices. Which one should you choose, right? So that's something we're going to talk about. So there's no silver bullet. That's why we're going to talk about both of these structures. There will be certain scenario where it will be more efficient for the array to operate, and vice versa for linked list, right? So we really got to see which scenario we are talking about, right? I'll get there. And we're going to talk about 2 sorting algorithms. Remember the 5 I kind of mentioned on day 1, right? When we talk about syllabus, insertion sort, selection sort, which we're going to talk about most likely Thursday. And later on, after reading week, we're going to talk about merge and quick sort, when we talk about more advanced recursion. And then the final one to talk about will be heap sort, right? So that's kind of the roadmap for the course. And for the linked list, we're going to see what it means to be singly linked and what means to be doubly linked. So this part here is really lots of fun. So you guys can bring your notebook, lots of drawing to do to really understand what's going on, right? Maybe from Thursday, maybe later part of Thursday or definitely Tuesday next week. And we're going to see the runtime comparison between array and linked list operations. We'll see some of them for array today. And for your assignment number 2, which will be released at some point next week, and assignment number 2 is going to be about linked list. So we're going to cover some basic one in the lecture, but you guys will have to really do lots of coding yourself, which we assume you kind of grasp some coding skill from 2030 in the previous courses. There will be something required called generic list, which I'll try to see if I can talk about it, or I will include resources in the assignment that I can look at. Okay. So these are the things we're going to talk about. Let's talk about array very quickly. Array, you know very well the definition, just a sequence of index element. Whenever you want to get to a particular index, under the hood, or behind the scene, you just have to calculate what's the relative address and go there, right? That's what you learned in 2031, you know, in the C course. And the size of an array, whenever you create the array, should be fixed. That means you can resize the array, but it's going to be some very expensive operation to do. Because every time you resize the array, you got some strictly larger array. You still want to copy over the old array into the new array. That copy operation is going to be expensive. All right? That's something I will also need to visualize a little bit later. And I want to give you guys some heads up over here. People still do array resizing quite often for the Java library collection. For example, let's say array list. They do have array implementation behind the scene. The way they talk about resizing, I believe, is something called doubling, right? So here, don't need to be troubled too much about increments or doubling. I just want to mention the two terms to you. So people usually, if they want to implement their data structure using arrays, they got two options usually, common options for resizing, either called the increments approach or doubling approach. One of them, if you try to argue about the average case, when I say average, it's more about expected value. Right? If you talk about average case, one of them turns out to be constant as opposed to linear, which is very efficient. Right? I'll see if I can give you some guidance about these two strategies. We'll see how the coverage is going to go for the lecture. Right? But for now, just heads up about these two. All right. So what will be the operation for the array? So you got accessing the array. In that way, you just calculate the address. That will be constant operation, big O of 1. If you just want to update some position there, that one there, just do some variable assignment, that will also be just constant operation. The expensive one comes whenever you want to insert something in the middle of the array, or you want to remove something out of the array. That's going to be some expensive operation. So what I want to show you is about inserting by diving into some details. And we can do the practice again about deriving asymptotic upper bound once more. We'll do that. All right, so code fragment that we're going to talk about will be this one here. Okay, we'll see. We'll definitely try to go as much as we can for this example here, and then we'll continue from Thursday. But we got 14 minutes. Okay, let's see how much we can do. All right, so here we got insert at. This is the method we are analyzing. That one there takes one input array and returns another array. Takes an array as input, returns an array as output. So this n here will be the size of A, right? Just our convention, just for easy analysis of the runtime. So this will be A.length. And then we got E and I over here. E and I over here simply say, I want to insert into index I, the element E. Okay, I'm going to show you an example. So this one tells me that I want to insert element E to index I. And we are making the following assumption. Okay, let's say if you got an array over here, let's say this is the array. If I say I want to insert at, I pass over here 0. That means I want to insert right in the beginning. On the other hand, I can also say I want to give the value n. Let's say, for example, I got 1, 2, and 3. I say I want to insert index 3. 0, 1, 2, 3. I want to insert it as a last. Right? So both 0 and n will be the extreme values, will be the bounds for I. So this is something important when we try to figure out the runtime. So this could be 0 less than or equal to I, less than or equal to n. 0 here means we want to insert first. And this one here, we want to insert at last. All right? So these are the two boundary values for I. All right? I would suggest we try to understand the algorithm a little bit. before we try to derive the running time. But again, in order for you to derive the bounds, you don't need to understand how the algorithm works. But let's do that anyway. So this is one example here, okay? This one here. If I want to insert, let's say the input array is Alan, Mark, and Tom. Okay, let me just keep track of the time. Good. Okay, sorry. Give me one moment here. Good. If I got Alan, Mark, and also Tom over here, right? That's the input array. You can see the size of the input is simply 3. I want to insert Jim at index 0. Index 0, as you can see, is over here. So think about the 0 over here is I. All right? So that means Jim should be inserted in the new array. Oh, by the way, before that, given that input array is of size 3, I'm going to create a larger array of size 4 with one extra slot for me, right? That makes sense for the new element. And then what's going to happen is, you can see after index I, which will be 0, what should I put over here? It should be whatever element that used to be in the input array over here. So that means Alan should really go to here. Mark should go to here, and Tom should really go to here, basically. All right? So what's going to happen is I'm going to have this index 0 in the input array should be copied to index 1 in the output array. Index 1 should really go to index 2. Index 2 should really go to index 3. This is exactly what you will see in this line of code over here. All right, I'm just trying to show you why it should be done that way. It's a very basic operation, just to shift everything to the right by one position. Right, so after that, I'm going to get over here, I'm going to get Alan, Mark, and Tom. So in this simple case, we just want to add Jin into the first index, index 0. Whereas all the original element will just be shifted to the right by one position, right? That's how it works. And let me just trace one more time. I'm going to trace the algorithm line by line, and I'll do another example, okay, altogether. Okay, let's take a look. The line, this line here, we are just creating a strictly larger array. So size 3 is now become size 4, right? I didn't really include this one in the list of primitive operation, but object creation is really a primitive operation, right? Just allocating memory. So you can think about this guy over here would just be 1, just this line. So I'm going to put 1 here, and I'm going to put it aside. Whenever we talk about object creation, by calling the constructor, big O of 1. Okay? Just creating the new objects, basically, okay, in this case. So line number one, this one here is good. So now we got different phases. We got phase number 1, phase number 2, and phase number 3. And eventually we return the array. So for the last line here is also going to be 1. Let's write it down first. And then we're going to analyze how phase number 1, 2, and 3 are going to be figured out. All right, so 1 here as well. Let's now look at phase number 1, which I'm going to highlight in green. This part over here. Right? This one tells me I am actually going to go from 0 all the way to I minus 1. How many iterations are there? I iterations, agree? What's I? Somewhere between 0 and n. So what's the worst case for I? N. All right, you can see the connection here, right? Okay, I'm going to write it down in a moment, but let's see exactly what's going to happen. Now I want to insert, I still got the same input array, Alan, Mark, and Tom. I still got Alan, Mark, and also Tom. I want to insert Jim over here into index 1. All right, you can think about index 1 is actually over here. Right? Index 1 is actually over here. What's going to happen is I know that Jim, after inserting, Jim should really go here. This one's easy, right? That one we agree. So this one here is really this middle stage, right? This one here is really just 1. Let's write it down first. What's going to be something you got to think about will be the before stage and after stage. if I want to insert Jim into index 1, that means anything that goes before index 1, for example, this will be I minus 1. We should copy that to here, before that. Anything that goes starting from index 1 over here, they should really go to here, after index 1. That's basically what we're doing, right? Good. If you see the conceptual idea, that's great. So I'm going to do some coloring over here very quickly, and then we'll figure out running time. Think about this one here. I'm just going to put it in blue. Okay? So what's going to happen is before index 1, we got Alan. Starting from index 1, we actually got Mark and Tom over here. So for this particular loop over here, it's actually going to copy whatever that's before index 1, which will be Alan in this case. It could be multiple in general. Copy this into over here. So it's going to be Alan. And when we move on to this particular loop over here, it's going to start from I plus 1. I plus 1, this is I, so this will be I plus 1. So this is I, starting from I plus 1. I'm actually going to say Mark should be copied over to here, and Tom should be copied over to here. Right? You can see this exactly 2 versus 1, and 3 versus 2, like a one-off indices, exactly over here. That's something I'll leave to you to really study. All right? So that one there, I'm going to get Mark over here and also Tom over here, right? So you can see exactly the correspondence over here, Mark and Tom, and also Alan. Right, that's very quick tracing, right? Didn't really go into 100% detail, but that's something you should be able to following the code line by line and then try to see how that works. And let's now figure out the running time, all right? Let's now do the following. Let me start with this one here. The body of the first loop, what will be this, each execution? 1, agree? Just array indexing and maybe some variable assignment, so just 1. But how many iterations do we have? As we said earlier, it's going to be from 0 to I minus 1. So that would be exactly I iterations. We know that I in the worst case is going to be n. So that means in the worst case, it's going to be n iterations. Right? So this is very crucial for you to realize over here. Okay, so that's the number of iterations for the first for loop. What about the second for loop over here? It's going to be from I plus 1 to n. Right? Let's specify the closed interval. We got I plus 1, n. All right, so now this one might be the one we need to apply the formula. How many integers do we have in this closed interval? Okay, anybody tell me? Not exactly. N minus I plus 1 plus 1. Okay? And so here we got n minus I, and we got minus 1 plus 1 cancel out, so only n minus I. All right, guys, it's okay to be struggling a little bit now, but you really got to make sure you kind of get it. Okay, so that's going to be n minus I iterations. And I'm going to actually write it down. All right, so now we got all the information we will need. And then we're going to figure out the running time. Okay, I'm going to put it right here. It's going to be big O of, so I'm going to be 1. So this will be, this 1 here is the 1 here. Plus, the number of iteration for the first for loop will be n. The body here will just be 1. N times 1. Plus, here we got this 1 here, right? Plus, the second for loop, the number of iterations n minus I. So we got n minus I, and then times 1 over here. And then finally, we got 1. Right, like that. And then, if you try to see that, what's the highest power? Well, you can see power of 1. This is also power of 1. Because n minus I times 1, just n minus I. would still be, something close to n. So overall, it's going to be n. Okay, you can drop all the lower terms, etc. So the final answer you will get will be big O of n. This one tells you, in order to really insert something into the array and do all the necessary copying, shifting, etc., it's going to be a linear operation. Okay, very important for you to really understand. Okay, and then you guys can try maybe insert add over here. So this one is the worst case for. So let me just give you some insight over here you can think about. This one here is really the worst case for the second for loop. And this one over here is really the worst case for the first for loop. Okay, I tell you just this one here. The reason that this will be the worst case for the first for loop, simply because you're going to do the number of copies that correspond to 3, which is the size of the input. Okay, and then as to why this will be the worst case for second for loop, I'll leave you to think about. All right, just give me 30 seconds. All right, so this one is good. And I want you guys to take a look at this the next slide there about sorting, and then think about if you know already how to distinguish between these 4 terms about sorting orders. That's something we have to get into next time. All right, thank you. I'll see you on Thursday.